Something impossible sits at the center of our galaxy. 4 million suns of mass packed into a space smaller than Venus's orbit. Everyone calls it a black hole. But ask one question: what stops that much mass from just collapsing into one, and astronomers go quiet? There's another answer. A ball of dark matter dense enough to fake a black hole perfectly. And it comes with its own built-in test. The first hint came almost a century ago. In the 1930s, Carl Jansky picked up a strange radio signal pointing straight at the constellation Sagittarius. Nobody knew what it was. Black holes were still just math on a chalkboard, barely taken seriously. Guesses ranged from star clusters to supernova leftovers. It took until 1974 for 2 astronomers, Bruce Ballack and Robert Brown, to identify it as one single compact object. Brown gave it a name: Sagittarius, a star. The theory of black holes had just been worked out. 2 and 2 got put together fast. Speculation grew that whatever sat there was gargantuan. Nobody could prove it. Not yet. For decades, the case looked closed. In the 1990s, astronomers tracked stars whipping around an empty patch of sky. One of them, S2, loops the center every 16 years at nearly 8% of the speed of light. Our own sun takes 200 million years to do the same. Only something immense could pull that hard. In 2020, the teams who measured it won the Nobel Prize in Physics. Their citation was careful: not black hole, a supermassive compact object. 2 years later, the Event Horizon Telescope imaged the region directly. A dark center, a bright ring of glowing gas bent by gravity. Case closed, right? Except it wasn't. The Nobel Committee's wording wasn't an accident. Nobody has proven Sagittarius a star is a black hole, not once. Black holes can't be seen, only inferred. Light that crosses the event horizon never comes back, so every image is really a shadow cast by something we assume is there. That assumption has cracks other scientists have poked at for decades. Boson stars, gravastars, dense shells of matter with no singularity at all. Most died quietly as the data got better. One didn't. In February 2026, a team from the Institute of Astrophysics in La Plata, Argentina, revived it. Their claim is that Sagittarius A star isn't a black hole. It's a supermassive ball of dark matter, dense enough, in theory, to fool every telescope pointed at it. Valentina Crespi and Carlos Argüelles built a model where dark matter behaves like a fluid made of fermions, the same particle family as electrons. Fermions obey one strict rule: no two can occupy the same state at once. Squeeze them together, and they push back. That resistance can build a stable, ultra-dense core heavy enough to match a supermassive black hole. Published in the monthly notices of the Royal Astronomical Society, their model matched the orbits of S2 and 5 other nearby objects to within 1% of the black hole prediction. Statistically, you cannot tell the two apart. Any theory chasing this mystery has to explain more than just stars. Since the early 2000s, astronomers have tracked a strange class of objects near the center called G objects. They behave like stars but look like gas, visibly stretching and changing shape as gravity distorts them. They might be dust-shrouded stars or compact clouds barely holding together. Whatever they are, any model of Sagittarius A star has to reproduce their bizarre, shifting orbits too, not just the tidy paths of ordinary stars. When Crespi's team ran the numbers, their dark matter core matched the G object's behavior just as well as it matched S2. That's not a small detail. It's the difference between a lucky coincidence and a real model. Here's what makes it more than a curiosity. This is the only model where the central object and the galaxy's dark matter halo are the same substance. Not 2 separate mysteries, one continuous structure, dense in the middle, diffuse at the edges. If true, it wouldn't just explain Sagittarius A star. it would tell us what dark matter actually is. 85% of the universe's matter identified, hiding in plain sight at the center of our own galaxy. The model isn't just elegant, it fits real data. In 2022, the Gaia mission mapped 1 billion stars and found something odd. The galaxy's outer rotation slows down faster than expected, a pattern called Keplerian decline. Most dark matter models can't reproduce that, but fermionic dark matter can, because the Pauli exclusion principle gives its halo a sharp edge instead of a fuzzy tail. That sharp edge naturally produces exactly the slowdown Gaia measured. Then there's the shadow. In 2024, a separate study showed a dense fermionic core lit from behind by swirling gas casts a shadow almost identical to the Event Horizon Telescope's image. Same dark center, same bright ring. From a distance, you genuinely cannot tell a dark matter core from a black hole. But one thing would give it away: a photon ring, light trapped in endless loops around an event horizon. Dark matter cores don't have one. Black holes do. Nobody has confirmed one exists around Sagittarius, a star, yet. Here's the strangest implication. If this theory is right, the center of our galaxy isn't a point of no return. Arguelles has said it outright. Point a spacecraft at Sagittarius A star, and under the black hole model, you'd be torn apart and swallowed. Under the dark matter model, you'd sail straight through. No event horizon, no death, just an extremely dense, extremely dark region made of particles that don't care you're there. Same silhouette. From a distance, completely different fate up close. Here's the part most coverage skips. This theory can prove itself wrong. Fermionic dark matter has a hard ceiling, a maximum mass fermions can support before collapsing anyway, into a black hole. Current estimates put that ceiling around 10 million solar masses. Sagittarius. A star fits, barely, at 4.3 million. M87's black hole doesn't. It's 6.5 billion solar masses, 1,500 times over the limit. Same shadow, same ring, and a mass that should be physically impossible under this model. Crespi's own team admits it. Their theory may be less likely than the black hole it's trying to replace. If Crespi and Arguelles are right, the fallout goes far beyond one galaxy. Standard cosmology assumes dark matter particles are heavy and slow. This model needs them lighter, stranger, and more structured than most theories allow. Other galaxies could lack central black holes entirely. And black holes aren't just gravity wells. In the standard picture, they regulate star formation, blasting out energy that keeps galaxies in check. Take that mechanism away, and astrophysicists need a new explanation for why galaxies look the way they do. Not everyone's convinced. Outside researchers call the idea intriguing, but stress it would need extraordinary evidence to unseat the black hole model. So far, both explanations survive. Neither has been ruled out. So how do we settle it? Not by flying a ship into the center, by waiting. In 2026, the star S2 makes its closest pass yet, tracked by an interferometer in Chile precise enough to catch a specific wobble, one that black holes produce and dark matter cores do not. Underground in South Korea, the NEON experiment is hunting for the particles directly, and NASA's proposed Black Hole Explorer could image the region sharply enough to spot a photon ring, if one exists. That could take decades. Two mysteries, one galaxy. Right now, nobody actually knows what is staring back at us.